So I'm going to be talking about big graph data science, and we've already heard a number of times about big data, the tsunami of big data, the avalanche of big data, the tidal wave of big data. You know, we're drowning in big data. A number of people have said that. But one of the things that I want to emphasize is the fact that data is not flat. In particular, big data is not flat. So I'm very much going to be following up on what Jennifer was saying earlier about the fact that the data is really richly structured. It's multi-relational, it's multimodal, it's spatiotemporal. There's all kinds of interesting links and structures in the data. The thing that's interesting from kind of a machine learning perspective and a data science perspective is oftentimes, so we start off with this wonderful graph, and what do? We take it and we flatten it and we put it in a matrix. And you know, why do we put it in a matrix? Because that fits most, not all, so I want to be careful not to overstate, but a lot of traditional machine learning algorithms and statistical methods assume that you have an IID sample where each row is an instance and you know, each of the columns is some sort of feature. And once I have it in this form, then I can stick it into you know, my MATLAB code, my R code, you know, or something more sophisticated and so on. But there's lots of beautiful algorithms, but they're making an assumption of having the data in this format. So what I want to argue in my little talk here, and hopefully Jennifer will sign up for this too, is that we need data science for graphs. So we need a new V. So we have volume, velocity, variety, veracity, and like sometimes 7 others. But we need one that captures this notion of the ties between things and the structure. And I actually managed to find one, vinculate. So this actually means the kind of ties between things. So in this talk, what I want to do is kind of go through very briefly some patterns that I think are really fundamental, very simple micro patterns that are useful when you're dealing with graphs and trying to do machine learning and prediction. I'm going to then talk about some key ideas where I'm going to talk about them hopefully at such a broad level that you know, no matter what your favorite tool is, what your favorite kind of ways of thinking about these algorithms can end up being useful. And then I'm going to be very, very briefly mention some work that we're doing in my group to address this. So for patterns, the patterns are super simple. The first one is collective classification. So just the really simple idea of I want to infer labels for the nodes in a graph. And I'm going to illustrate all of these with kind of little simple problems. So here's my social network. I have all kinds of links, and I want to label the nodes with what their political persuasion is. And usually what happens is that I have some of the nodes labeled, and then I have some where I have question marks, and I want to, in some smart way, be able to infer these unknown labels for nodes. So again, super, super simple problem. Probably the simplest problem, even simpler than PageRank to do on a graph, is just label the nodes. The next problem has to do with edges. So link prediction, predicting the existence of edge in a graph. And let me illustrate that with a kind of slightly more complex problem. So in this setting, in this example, I have some sort of communication network where I have people, I may have their communications, and I have some observed relationships. So I've observed who sent messages. I may have some information about co-location. You can think of all kinds of other things that I could have too. And then what I want to do is I want to predict links but I want to predict links that have a different semantics than the links that I've observed. So an example would be, try and infer the organization hierarchy, who reports to who. And I'm framing this as kind of a 0-1 predict a link or not, but oftentimes this is very closely related to ranking. And so you can think of a lot of recommender systems as recommending links between users and products, or recommending friends and so on. And then the last little micro pattern that I want to mention is entity resolution. Entity resolution is you have a graph, you're trying to figure out which nodes refer to the same underlying entity. And I like to illustrate this with, this is my favorite problem. This is actually a little fragment of a real data set, supposedly extensively hand cleaned. It's a co-author network, so the nodes are authors, the links are co-authorship links. But if you look at it even just for a little bit, you start seeing that there's actually a lot of issues with this graph. In fact, we were talking about dirty data and cleaning data. This is an important step to take into account, because if you look at the before network and you calculate any kind of feature, any kind of statistic on it, it's going to be completely wrong. And there actually are a number of real-world examples where people have taken a network that has had entity resolution issues and gotten incorrect scientific conclusions out of it. And if anybody wants these examples, I would love to go into them now. I won't, but I'm happy to give them. Okay, so again, these are really simple problems. But really, my favorite graph analytic or graph inference problem I call graph identification. And that is to kind of take all these things and do them all at once. And again, this is related to kind of network reconstruction. So how do you take some noisy network, some noisy observational network, then how do you do the inference to figure out what the real network is, the cleaned up network, the network that you want to do your science on. So I want to talk really briefly about what I think are some key ideas that kind of any approach that's going to deal with these kind of graphy problems needs. And the first one has to do with that flattening bit. What is happening in that flattening? Usually you're doing something about constructing the features. And the biggest thing, I think Monica said this, about kind of how do we extract more signal and more kinds of features that you can use in a graph setting? Well, you want to use something about the structure in the data. So you want to use something about the schema. You want to know something about the kinds of relationships that are in the data, which ones make sense, how to aggregate them. And there's different things that make sense. If you're trying to make a node level prediction, certainly you want to use all the information you have at that individual node. But then on top of it, you can do things that look at the relational structure and create some sort of feature that takes that into account, something about the clustering coefficient locally. There's all kinds of things that one can do. And then for link prediction problems, whether it's entity resolution or a ranking kind of problem, you have pairs of nodes, and you're looking at pairs of nodes and trying to figure out what are the kinds of features that make sense to construct. And all of this is wonderful. You can use all your KR, knowledge representation information, your data schema information, your semantic web kind of information to construct these features. And that's actually what's most commonly used in industry. But the con is that flattening process. You've made incorrect independence decisions, and there's other issues as well, but you're also, by making these independent decisions, you can't have one depend on another. And that's the next idea that I want to talk about, collective reasoning. And let me go back to the examples from before and try and illustrate it there. So, back to our political persuasion example, I'm trying to figure out the political party of an individual. Well, certainly I want to use all the local information. So, I want to do things like, okay, let's look at what campaigns they contribute to. Let's look at their status and their tweet updates. Let's look for phrases that are highly indicative of a particular party. But from a network perspective, I also want to be able to, take the labels that I have and do things like say, okay, well, if a friend votes for a particular party, maybe that means I'm more likely to vote for that party. If my spouse votes for a particular party, then I'm even more likely. And be able to kind of take this kind of networky local information and in some way infer all of these missing labels, but do it in a way that's joint so that I don't just infer them independently, but I figure out for the set of labels, what's the most probable collection for all of the unknown labels. And there's a bunch of different algorithms for exactly how to do this, but the important thing is to not do it in this flattened way. From the entity resolution example, doing something where, again, we can collectively reason about, we're trying to figure out if A and B are the same. I may look at the strings that are their names and see how similar they are. But then more interestingly, I can have this kind of recursive definition that says, well, if their friends are similar, they're more likely to be the same. And if the friends of their friends are similar, and so on. And then finally, oftentimes in entity resolution, you want to have this kind of transitive closure kind of thing where you say, if A and B are the same and B and C are the same, then A and C should be the same. All of this requires more complex kinds of reasoning. And it's hard because you have outputs that depend on each other, and we need scalable ways of doing this. And then the last little idea is lifted inference. The idea that when we have this big graph, we don't want the parameters to blow up with the size of the graph. We want to capture common patterns of interaction. How do we parameterize the model in a reasonable way to do that? Now, HMMs have a way of doing it first sequence. When you have a rich graph, it's really interesting and challenging for doing this. Again, this is something I'm very interested in. There's a bunch of approaches from the statistical relational learning community that have tried to do this. This is a survey article that goes over some of them. So let me get to the last little bit, which is a tool. And this is a tool that's being developed in my research group. Actually, Steve Bach is one of the lead architects on this. He just graduated with his PhD. He's doing a postdoc here in Chris Ray's group. So if this seems interesting to you, he's local. Come look for him. There's actually a bunch of folks involved in this project. They're in the audience, so you can catch them as well. And this is what pains me as an academic. Now, this is a slide that I would normally, in a real talk, I would go into an hour on, but I'm going to do it in a single slide. So PSL is a probabilistic programming language that's specially designed for building these kinds of models. They're a form of Markov random field, but a special form of Markov random field for capturing these kind of collective reasoning kinds of problems. The kind of key thing about them is that they're highly scalable. We get map inference, so figuring out the most probable assignment for all of the random variables to be a convex optimization problem. How do we do that? That is some really nice results that we've just gotten in the past year, showing like 3 different ways to get to the same optimization problem. Whenever you get to something 3 different ways, I think of it as being, fundamental. So I'm really excited about this. It's actually cool. We can also use many of the most state-of-the-art optimization techniques for making it even more scalable. We're kind of just starting this work. It outperforms discrete MRFs by scaling orders of magnitude. So we can do several orders of magnitude, larger problems. And then the interesting thing is it actually improves in terms of performance in terms of accuracy as well. We've applied it to a whole range of problems. And again, this is something that I'd love to talk more about, problems in computer vision, problems in natural language processing, a lot of problems in computational social science. So how do you make use of sentiment, trust, and so on, and a lot of things for information extraction, so knowledge graph extraction and so on, some biological networks, drug target prediction, and so on. And it's open source. It's available from that URL. There's data, tutorials, and so on. So hopefully I managed to sell it to you in less than an hour-long talk. So popping up, I think we can agree we're drowning in big data, and hopefully we can agree that a lot of that data is highly relational, and that we really need methods that can kind of question some of the old assumptions about independence, and how do we kind of construct richer models that are still parameterized in a reasonable way that can take this into account. How can we deal with the bias in the data, the noise in the data, privacy, and all those kinds of things. So I think there's a lot of exciting opportunities for new theory and algorithms in this space. And there's tons of really interesting applications in industry and science and societal problems. And I want to close with a little plug. As we said, UC Santa Cruz is that way, about 40 miles. It's really nearby. The campus itself, I got my PhD at Stanford, but it's really beautiful. There's redwoods, the view. And we have a new data science program. We're looking for students. We're looking for collaborators with companies. And we're also hiring in a number of areas. We have data privacy, data security, and information networks are some of the areas we're hiring faculty. So, thanks.
Fantastic. Thank you.